going to talk about geologic time, one of the biggest issues that we confront as creationists, and one of the most challenging ones for us to accommodate. So before we start, let's bow our heads for prayer. Father, we thank you for today. We thank you for the opportunity we had to share with our neighbors and friends about the work we're doing here. We ask your blessing tonight upon this class, that you will give us wisdom and understanding that we don't have in ourselves. We love you and we praise you in Jesus' name. Amen. We've already reviewed the things that science cannot do and the things that science can do, but just briefly, going over them again for purpose, radiometric dating is a problem for those who believe in creation. It's a big problem. It's one that is in our faces all the time. We can't forget it, and we don't have any really good answers for it. I was asked this question a number of times today as we were talking with our friends and neighbors about the issues concerning the geologic past. And I was willing and quick to tell them that radiometric dating is a problem for me because I'm accepting the Bible account of creation a few thousand years ago. And radiometric dating, no matter how you cut it, seems to suggest time that is much, much longer than what the Bible would allow. There are other dating methods besides radiometric that also seem to give extended time, and these also would need to be evaluated and accommodated one way or another. There also were issues with the fossil record, and we talked about these, the orderly fossil record, the hominid record, and we could go on and talk about other problems as well. But this is sufficient for us to evaluate and look at the other side of it and talk about the origin of life, which is a big problem for evolutionists because they have no clue how life could have been generated apart from a creator God. And it doesn't matter who they are. They can have Nobel Prizes, they can have world recognition of their names, but they have no clue how life came into existence. So you'd think there'd be room for a little humility on their part, and hopefully there is some, but more often than not we run into the problem of resistance to consideration of problems. So origin of life, that's one for the creationists. The fossil record also has some aspects that are favorable to creation. The sudden appearance of fossils in the Cambrian after the Precambrian with no fossils. This is a serious problem for those who believe that life originated from previously existing forms because there aren't any. There also is the question of general absence of intermediate forms. We do not see the so-called intermediates between various fossil groups that we would expect if evolution was the origin of the life forms we see today. Tonight we're going to deal with some issues in sedimentology and catastrophism, evidence for extraordinary events that is concordant with the story in the Bible, and a general lack of evidence for time. So we're going to cover these and talk about them. We talked last time about molecular biology and what it tells us about where we came from, and it certainly does not support the idea of spontaneous origin of complexity. So the kind of thing we see looks something like this. We see there are issues on the side of evolution, there are issues on the side of creation. It's not like this and it's not like that, it's like that. And that tells us that we can never learn where we came from science, because there are problems on both sides. There are questions we cannot answer on both sides. So those who take a position on origins are not doing so because of the scientific data. They're doing so because of something outside of science. And that something is generally going to be philosophy or religion or some other aspect of their lives. So people are making a decision, and then they're looking for evidence to support it. So we'll take a look at that evidence now, starting with geologic time. So here is the geologic time scale, and the standard reckoning of these periods that you see over here on this side. The time in years is given over here, 490 million years for Cambrian Ordovician, 443, and on up. And all these dates are testified to by radiometric dating and the outcome of radiometric dates. So we have two different kinds of time. We have things called relative time and things called absolute time. And relative time is that one layer sits on top of another. For example, the Lance Formation is underneath the Fort Union Formation. So which is the oldest? The Lance is the oldest, that's right, because it's underneath. How else would it get underneath if it wasn't there first? So we say that's a relative time indicator. It doesn't give us any idea whether we're talking about days, weeks, months, years, hours, seconds, or whatever. But the other aspect of this, absolute time, this requires an understanding of the principles of radioactive dating. So we're going to take a quick look at that and talk about the age of the Earth. Radioactive dating is a process that takes place when the nucleus of an atom spontaneously changes. It appears to be independent of the normal parameters that we would think would apply, like temperature and pressure, and anything else in the physical environment does not seem to be able to affect the rate of nuclear decay of radioactive atoms. In some cases, the nucleus gets smaller. In all cases, the kind of the atom is changed. It happens at known measurable rates at the present time. Here's an example of alpha decay, one of the three major types of decay. In alpha decay, an atom, a parent atom, gives rise to an alpha particle which consists of 2 protons and 2 neutrons. So the atom is losing 2 protons and 2 neutrons. It becomes some other atom. So it may start out uranium and end up thorium, or it may start out uranium and end up something else. But in this case, it's going to end up being thorium, I believe. If I'm not mistaken, I'll have to look at the decay scheme in a minute. So an alpha particle is made up of 2 neutrons and 2 protons. Every time you change the number of protons in an atom, doesn't matter what the atom is, when you change the number of protons, you're making a different substance. So if you have platinum, for example, platinum has 91 protons. If you add one more proton to it, you can make gold. So if you bombard platinum atoms in a cyclotron with a proton, you can make gold. So we should all be rich, right? Well, wait a minute, platinum is more expensive than gold. So that's not going to get you very far. But just bear this in mind, we're actually changing the kind of substance that we're dealing with. This is major, major. It means that all substances that we know of, everything in the chemical periodical table, is made up of the same stuff, protons and neutrons, and the number of protons determines what it is. Is that clear?
Sure.
So if you have a carbon atom and it has 6 protons and 6 neutrons, it has an atomic weight of 12, it has an atomic number of 6. If you add a proton, what's it going to be? What's next in the periodic table? Nitrogen, that's right. So it's going to become nitrogen. So you actually transmute elements by adding a proton or taking away a proton or more. Here in this case, you're taking away 2 protons and at the same time 2 neutrons. That alpha particle happens to be a helium nucleus. So you're actually taking a helium away from the parent and generating a different compound. Atomic number goes down by 2, atomic mass goes down by 4, and you now have a different element. Beta decay is more common in our thinking, this is the way radiocarbon behaves. An electron is ejected from the nucleus. A neutron becomes a proton. The atomic number increases by 1. The atomic mass remains essentially the same since electrons have almost no mass, or very small mass. So a neutron becomes a proton. Atomic number increases by 1. So a carbon atom becomes a nitrogen atom. Electron capture is just the opposite. A proton becomes a neutron in the nucleus by bombardment with an electron. The atomic number decreases by 1. Atomic mass does not change. So this process, whenever it happens, we call radioactive decay. And so we are changing what the element is. Here are some examples of decay schemes that are very familiar. Potassium to nitrogen decays back to nitrogen. So potassium-14 is decaying to nitrogen-14. Half-life 5,730 years. Range that you can use it for is about 60,000. So somebody asked me today, what about carbon-14 dating? That's the most common thing lay people say. And what it tells you is that they really don't know anything about it, so whatever you say is going to be better than what they have. But I told them that potassium argon, the carbon-14 dating is not much of a problem. It's only dealing with a few thousand years. Potassium argon is a little different. It's 1.25 times 10 to the 9th. 10 to the 9th means billion years. 1.25 times 10 to the 9th years. That's 1 billion years is the half-life. That means half of the atoms that you have today will still be there after 1 billion years. So you better have a lot of atoms if you're going to figure out something with this method. So let's take a look at carbon in detail. Carbon has 6 protons in the nucleus. The most common isotope is carbon-12. That's 6 protons, 6 neutrons. Some carbon is carbon-13. That means they have an extra neutron in the nucleus. Still 6 protons. Remember, the important thing that determines what the atom is the number of protons. So 6 protons and 7 neutrons, well, that's kind of out of balance, isn't it? But that extra neutron adds weight to the atom and makes it different, so we call that carbon-13. Carbon-13 is stable. Once you make a carbon-13, it stays a carbon-13. It does not break down. If you add 2 neutrons, then you have carbon-14. So you have 6 protons, so it's still carbon, 8 neutrons, so it weighs 2 extra besides normal carbon in the nucleus. So this is unstable. So the first is stable, the second is stable, the third is unstable. It's radioactive. It's going to break down with time. So here's an example of carbon-14 breaking down. Here's the nucleus. Notice there are 1, 2, 3, 4, 5, 6 protons, and 1, 2, 3, 4, 5, 6, 7, 8 neutrons. And now we're going to have that atom decay. It loses an electron, and it becomes this thing over here. But count the number of protons, 1, 2, 3, 4, 5, 6, 7. 7 protons, that's no longer carbon, is it? That's now nitrogen. Nitrogen's the next element in the table. And it's 7 neutrons makes it normal nitrogen. So carbon-14 breaks down by loss of an electron from a neutron to form a proton, and it now becomes normal nitrogen. Carbon-14 spontaneously decays to nitrogen-14 at a constant rate. The rate is constant because it's a stochastic process, is not controlled by any environmental factor, so it's just going to break down when it breaks down. One atom, if you pick out an atom and you say, okay, you're supposed to wait 5,730 years to break down, that's one half-life, is it going to pay any attention to you? No, because some of them are breaking down right now. And that's why you can get disintegration right now. So you make some carbon-14 and it's going to start breaking down right away. Some will break down now, some will break down in 5,000 years. some will break down in 10,000 years, and so on. And you can't ever predict which atom is going to break down and which one isn't. The amount of time it takes for half the parent isotope to decay is called the half-life. So that's something we can measure. Again, we don't really understand the process, why it is that this particular atom breaks down at this particular time, but we can measure something called a half-life. And we can graph this on a decay curve. Here you see a curve of percent of parent isotope versus time in half-lives. So after one half-life, that's 5,730 years, right here, 50% of it's gone. What happens after two half-lives? 50% of what's left will break down, and you'll have 25% of the original amount still radioactive. After another half-life, it'd be 12.5% of the original parent, and you now have three half-lives, and so on. So that's the way radioactive disintegration works. Here you can see it occurring, and eventually you get so few atoms that it's essentially unmeasurable. So you can no longer, after 5 or 6 half-lives, you can no longer measure the amount of radiocarbon present, so you say the sample is dead. So after 5 or 6 half-lives, it's dead. So you can only go back so far with radiocarbon, and the half-life is 5,000 years, so you can go 5, 10, 15, 20, 25, 30,000 years. That's getting near the end of live radiocarbon. The other thing that happens is the daughter builds up as the parent goes down. So each half-life increases the amount of daughter and it decreases the amount of parent. The parent would be carbon-14. What would the daughter be? Nitrogen-14. How are you going to measure nitrogen-14? It's like being in the ocean trying to measure water. Nitrogen-14 is all around you. It's the most common element in our air. And if a radiocarbon breaks down and makes a nitrogen, you're not going to be able to detect it. So the only thing you can do in this case is measure the parent. That means you have to make an assumption about how much parent was there in the beginning. Okay. Here is the way radiocarbon is formed. This is really important to understand. A cosmic ray comes into our atmosphere. It hits atom of, say, nitrogen. That's what it's mostly going to hit because 80% of the air is nitrogen. So it's going to hit a nitrogen. It's going to knock out some neutrons. One of those neutrons will hit another nitrogen, and it will cause a proton to leave, and that will make a radioactive carbon-14. So the neutron knocks out a proton, and so the number of protons in the nitrogen is now what? Number of protons. If you knock out a proton, they're going to be 6. And if there's 6 protons, it's what? Carbon-14, that's right. So it still weighs 14 because it's picked up a neutron and lost a proton. So it's now radioactive carbon. So that radioactive carbon will now interact with oxygen in the atmosphere, and it will make carbon dioxide. Carbon dioxide will then be absorbed by plants. The plants will be eaten by animals. And so your meal, your lovely meal that you had tonight, delicious though it was loaded with radiocarbon. So you are acquiring more radiocarbon every time you eat. And as long as you're alive and keep eating, and those are kind of go together, as long as you are keeping eating, you keep bringing in more radiocarbon, and so your body is always in equilibrium with the environment. But what happens when you die?
You stop eating, and that amount of carbon-14 in your body starts to not be absorbed anymore. It actually disintegrate.
Okay.
After you die, would there be any type of transfer from the soil you're buried in?
That's a good question. And that's an assumption that's often made without any evidence, is that there's no transfer. But what happens when you die is you're no longer taking in more radiocarbon. So you're no longer eating, you're not taking in more radiocarbon, you're just you. So if they seal you in a casket and put you in the ground, you're just going to sit there and your radiocarbon's going to break down. So after 5,700 years, how much radiocarbon will you have left? Half. That's right. That's one half-life. After 2 half-lives, 11,000 years, how much radiocarbon's left? Quarter. After 17,008, and after 22,000 to 16. So that's the way radiocarbon dating works. So you take this thing out of the ground, you date it, you get 22,920 years. You say, okay, this is 4 half-lives old. So 4 times 5,720, that's about 22,000 years. So that's how you date with radiocarbon. Is that clear, or are there things I can clarify? We're going through this very quickly because we're not really focusing on radioactive dating. We're going to look at other ways of telling time. Yes?
So how did people in the first place figure out the half-life of carbon? Would they try to test it at a smaller scale and then try to make a graph for it with the data that they have?
Okay, you take 1 gram of radioactive carbon-14, pure carbon-14, and then you let it sit and you measure how much it's decaying. And you may do this for a day, a week, a month, a year, 10 years, 100 years. The longer you measure it, the more accurate you get. But that's the way it's done. You just measure the decay rate of the, by knowing how many atoms are there and then counting how many decays take place. Is that reasonable? Okay. All right. There are other methods that we'll just take a brief look at, but let's just look at the assumptions. We assume the decay rate is constant over time. It's unaffected by pressure and temperature, that a single daughter product is involved, that no parent or daughter atoms have escaped or been added. The starting amount of daughter is 0. Starting amount of parent is known. How many of those do we have problems with? Well,
the starting amount of daughter is 0 because nitrogen-14 is a pretty common.
but we're not measuring nitrogen, so that doesn't matter. In this case, it does matter in other ones. Okay, below that though, there's one, the starting amount of parent is known. How can you ever know the amount of radiocarbon that's in a organism that lives sometime in the past? Can you ever know? The only thing you can do is measure how much is there now and count backwards and assume that you know what you're doing. But you never can. Decay rate is constant over time. Well, it seems to be constant today, but how about this over time part? Do we know for sure that the decay rate has always been the same? The second one, decay is unaffected by pressure and temperature. There are some small effects that we know about. For example, very recently there have been some studies where people are measuring, that's all they do is just measure the rate of decay of an isotope. So every day they measure it and write it down, or it's automatically recorded. So over a period of time, they began to notice that there were some variances that were cyclic. And they tracked those down, and they found out that when the Earth is closer to the sun, they get a slightly different decay rate than when it's farther away. Nobody really knows why, but it's interesting because it's not supposed to change. So what's happening to it when it's closer to the sun? We don't know. This is a fairly recent observation, and I don't think the answers are in yet. There may be other assumptions we haven't even thought of yet. All right, go back to the chart here. Let's take a look at potassium argon because the assumptions are a little different there. Potassium is very abundant in rocks. There's lots of potassium in most rocks. So there's lots of isotope to measure because we're going to measure the amount of potassium-40. Potassium is 39. Normal potassium is 39. Potassium-40 is radioactive. It decays to calcium-40 most of the time. Unfortunately, calcium-40 is normal calcium. And there's lots of calcium in the rocks too, So you can't tell calcium-40 from decay from calcium-40 that was present in the rocks as calcium-40. But 11% of the time, the electron capture occurs, causing potassium-40 to decay to argon-40. So it goes from potassium with 39 protons and neutrons back to argon-40. So it moves from potassium back to the beginning of the previous row. So that looks like a promise because argon-40 is a gas. So if we can just extract the gas from the sample, measure the amount of gas, we can get an idea of how much potassium decay has taken place. But it's only 11% of the time, so we may have to do this about 11% of the time. We assume that the potassium goes to argon. Let's just look at these assumptions. Decay rate constant over time. Again, the same applies to this. It seems like it is in our experience, but has it ever changed? Decay is unaffected by pressure and temperature. It seems like that's the case, but has it always been that way, or is it always that way, or is there something in the physical environment that might affect the decay rate? Single daughter product is involved. In this case, we know that's not true, so we have to make allowances for that. No parent or daughter atoms have escaped or been added. Well, that's a real problem because these rocks coming out of the middle of the earth, molten, and then consolidating, can have lots of argon-40 incorporated into them, so there can be lots of argon around. So we try to compensate for that by other methods, but it's certainly not true that the no parent or daughter atoms have escaped or been added. That's very much an assumption that generally is going to be wrong. Starting amount of daughter is 0. That's an assumption that's generally going to be wrong. Starting amount of parent is known. Okay, there you are. How do you know how much potassium-40 there was in a rock that's supposed to be 250 million years old? Give me a clue. Well, you'd have to assume that the decay rate is constant, wouldn't you? Then you could work back and figure out how long it had been if it was decaying at the rate that generated the amount of argon you find in the rock. But you can't ever know that. So geologists try to compensate for that by choosing a standard somewhere back in the Devonian, and they say, okay, this is 350 million years, and this is the amount of potassium that's left, so we can assume that we know how much was there to start with. There may be other assumptions as well. Several ways are known to calculate absolute ages. Most involve radioactive decay. All have specialized applications. All have certain limitations. So no numerical age is truly absolute. This is a quotation from a very well-known geologist, a stratigrapher. He says, at present, physical dates do not stand on their own. They must be compatible with stratigraphy. You can't accept a radioactive date that gives you the wrong date. Stratigraphy has also served to highlight flaws and the relevance of unexpected factors in some physical procedures. So-called absolute dating is a misnomer, for physical dates provide numerical approximations, preferably considered within and constrained by what? Stratigraphic framework. So if your deposit is Devonian, then the dates should be Devonian. And if they're not, then what's right? The date or the stratigraphy? The stratigraphy, that's right, because the fossils are there, and we know the fossils evolved so many million years ago. So this is a severe constraint, and this is why you don't ever use the word absolute dating, because it's a misnomer according to R. Twydale. All right, so what can we do with science? We can look at the natural world. We can test ideas about the natural world to see if they work. If you're successful as a scientist, you can attract other people to your ideas. They may be interested in your ideas on origins as well. And besides, science is fun. Science is a lot of fun. And my daughter claims that I've never worked a day in my life because I've been doing science. Well, I do work. And some things are not fun, like grading exams. The most common interpretation of radiometric data would take life on the Earth far beyond the biblical time frame. You got that? The most common interpretations of radiometric data, that is millions of years, would take life on the Earth far beyond the biblical time frame, which is thousands of years. Although progress is being made, efforts to resolve the discrepancy head-on have not thus far been fruitful. We don't understand how to explain radiometric dating away. Certain features of the geologic record seem to contradict conclusions based on radiometric dates. And that's what we're going to look at now. What things in the geologic record seem to contradict the conclusions based on radiometric dates that the Earth is hundreds of millions of years old, that life on the Earth is hundreds of millions of years old. Is that clear? That's what we're going to look at. Okay, so how can we detect time in rocks? If the deposition of sediments that made up these rocks here in the Lance Formation occurred over millions of years, what features in the rocks would confirm that? Let's suppose the Lance Formation accumulated over 12 million years. How would we know whether it was 12 million years or if it happened in a fortnight? Which is how long? Fortnight's 2 weeks. Okay, that's number one. What kinds of things? I want you to be thinking. What would you see in these rocks if they really had deposited over millions of years as opposed to in a few days or weeks? Number two, if the sedimentary processes were occurring much more rapidly, how would we know that? How would we know that it wasn't just accumulating slowly over millions of years? More than 10 years ago, Dr. Brand and others set out to examine the rocks of the Colorado Plateau to see what they would tell us about the time required for deposition. Colorado Plateau was chosen because it's nearby, it's easy to get to, has a dry climate, and the rocks are well exposed. How about South America? How about in Ecuador? Could we study the rocks there?
Sure.
You can't see them. They're all covered with green stuff that we call fuzz. You know, if you can't see the rocks, you can't study them. And if you go into a tropical area of the world, it may be pretty. There may be lots of nice flowers there, but you can't see the rocks. And that's why a lot more geology is done in the Southwest than in, say, the Northeast, where you have the mountains all covered with this horrible green stuff. Yes?
Why would removing the green stuff, like how would it affect the rocks underneath it?
Well, you could see them. You can't see them if they're covered with green.
Yeah, so if we were to study it, why can't we just remove all the green stuff?
Great. How are we going to do that? Do you think they'd let you cut down all the trees and kill all the bushes and then you could study the rocks? It's easier to go to the Southwest where you can see them. There's no plants there, so you see the rocks. Does that make sense? So geologists generally study parts of the world that have well-exposed rocks. We work down in Peru. Why did we work in Peru? Because the rocks, there's no rain there. It never rains. There's no green stuff on the rocks. So we can see the rocks, we can study the rocks, and we can draw conclusions about them. All right, here are the issues that we're going to cover. Number one, sediments appear to have accumulated rapidly. Let's talk about that one first. Here we see an outcrop of Moenkopi Formation in Arizona, or actually it's in Utah. And the question is, did this accumulate in 10 million years like radiometric dating tells us, or was it a few days? How would you know? What would be the difference if it had been one way or the other? There are three ways we can tackle this problem. We can measure the rates in modern environments, find out how fast they were, assume that the rates in the past were similar, and then get a rate based on these assumptions. That's one thing we can do. Number two, we could refer to some external information about past time and apply that to the sedimentary layers. We could use radiometric dating methods to get time and measure thickness and then determine a rate based on these assumptions. So if this is 10 million years, we measure how thick it is, and then we assign a rate based on that. The other thing we could do is use the Bible time frame and measure thickness of sediments and determine a rate based on these assumptions. This stack of sediments is 1,200 meters thick, accumulated in a couple of days. You could say based on the Bible. Or number 3, we can use calculations based on the behavior of sedimentary particles. That is, we can look at what would be necessary to get these particles to move into this basin and be deposited. What kind of answers do we get? Well, let's take a look. Here's a modern depositional environment. This is the Gulf of Mexico. Here's the Mississippi River coming out into the Gulf. Notice that it's growing way out in here because we constrain it with levees. We can measure rates out here in the Gulf of Mexico. It's a depositional environment. Rates of accumulation of sediment with actual measurements. We can put a stick in the ground, come back in a year and see how much there is on the stick. Rates in centimeters per year determined in a variety of environments where sediments are actively accumulating vary from less than 1/10 to more than 2 centimeters per year, most often closer to about 1 centimeter per year. So in the modern environment, we get accumulations at about that much in a year's time. So in 10 years, it's going to be that much. 100 years, a meter. So that's the rate that we're looking at. So we put it on a log scale. Where is 10 to the 1 centimeter on a log scale is what? 0, right? Log scale 1 is 0. So there you are, 10 to the 0 power is 1. All right, that's the modern rate. Now let's look at the fossil rate determined by using radiometric dating. Here's an example, 10 million years for this pile of sediments. We determined how many meters of sediment it is divided into the millions of years. And lo and behold, we get a rate that is somewhere between 1/10,000th of a centimeter to more than 1/1,000th of a centimeter, usually about 1,000th of a centimeter per year. Do you see something wrong here? In one case, we get 0, 1 centimeter per year in the modern environment where we can actually measure it. Here, where we calculate based on radiometric dating, we get 10 to the minus 3 centimeters per year. Do you see something wrong? The rate is way too slow, 1,000 times too slow. All right, let's go on and look at the next assumption. Sedimentary rates from the biblical narrative. 1 year of extremely high rates followed by gradual reductions to present. Rates in centimeters per year could vary from less than 100,000 to more than 200,000, perhaps averaging 150,000 centimeters per year. That's way over here. That's 10 to the 5 times the modern rate. Do you see a problem with that? No, because the Bible tells us that that's what happened. So that's not a problem in the same sense that this is a problem over here. So let's go on and look at the next rate. The rate based on behavior of sedimentary particles gives us rates of accumulation of 2,000 to 10 million times faster than the rates based on radiometric time. This is from a paper published by these two guys right here, where they actually determined in order to move this particle to this place, you had to have this rate of movement, which implies this rate of sedimentation, and that is 10 million times faster than this rate we saw over here. So here you have a rate somewhere over here based on sedimentary considerations. That's science. That's something you can't really assail. And so that's good data. So it looks a lot like, more like this is closer to the rate the Bible gives us than it is to either the modern rate or to this rate over here. So here is a summary. Modern depositional rates are 1,000 times faster than fossil rates, calculated from radiometric isotope dating. Biblical time frame gives rates that are 10,000 times faster than modern rates and 10 million times faster than fossil rates. Experimental sedimentation studies suggest rates 2,000 to 10 million times faster than fossil rates. So you've got radioactive determinations giving you this number, modern measurements giving you this number, and both sediment behavior and biblical chronology giving you this number over here. Do you see anything wrong with radiometric calculations? Well, geologists aren't going to sit back and take this without kicking back. So a friend of mine, Pete Sadler, who studies this kind of stuff, I should say an acquaintance of mine, he's somebody I talk to once in a while, he says that what's happening is this stuff is depositing at the modern rate, 1,000 times faster than the fossil rate. It's depositing at that rate, and then it's all eroding again, and then depositing again, and then eroding again, and then depositing again, eroding again, and depositing again, eroding again. And this is happening over and over and over and over and over again, so that the rate actually looks 1,000 times slower than it actually is. It's depositing at the modern rate, but what happens is every time it deposits some, then some erodes, then deposit, erode, deposit, erode, deposit, erode. So that's what he says. Now, is there any evidence for that? No, there's not. So why do so many geologists hang on to this idea? We'll show you how little evidence there is in a minute. But for now, just take my word for it. There isn't evidence that supports Sadler's ideas. All right, sediments appear to have accumulated rapidly. It sounds to me like that one's in favor of short time. Sediments do not appear in equilibrium with the environment. What do I mean by that? Well, let's take a look. We're going up here on the Colorado Plateau again. We're going to teach you a little sedimentology first. So we call it bredimentology. Each one of these pieces of bread represents a layer of sediment. So we have one layer deposited. We deposit another one on top, another one, another one, another one, another one. Okay, there you have 6 or 7 layers of sediment. 1, 2, 3, 4, 5, 6 layers of sediment. How do you know whether these two are deposited slowly or fast? Well, let's go back to where we started. And let's just say that there was a lot of time before the next layer got on there. So what's going to happen? Pretty soon you got mold on your bread. Then maybe you have a little mouse come around and start nibbling on it. And so you have all these evidences for the passage of time. All right, pay attention to that now. That's your cue as to what would happen if there was a lot of time during the depositional process. All right, so we bring the next layer and put it on there, and we put the rest of them on. Now we look at this stack of sediments. We say, well, that doesn't look like any time there, doesn't look like any time there, doesn't look like any time there or there. But when I get down here, look at that. It's moldy and it has bite marks out of it. This must have been exposed for a period of time before this layer got on top. Is that computing with you? Okay. Another example is what happens if some sediment is eroded away. So we'll just allow erosion to work here, cut away some of this stuff. And now we will put the next layer on top. And lo and behold, you can tell that there was time for erosion to take place here. And the next layer that came on top is there. And then we can put the other layers on there. And you can see that between this layer and this layer, there was some erosion that took place. Now, mind you, erosion doesn't take much time if it's soft sediment. So that's an important consideration on our side. But we ought to be able to see this if it's deposited slowly. So what do we see when we look at the sediments? The vast majority, and here I'm speaking from years of experience of working out here, measuring these sediments, centimeter by centimeter, tens of thousands of meters of sediment. The vast majority of the sediments show no evidence for time. They show no evidence for erosion. They show no evidence for disturbing of the sediments. What do I mean by that? Well, here's a layer of sediment, and you can see it has all these fine little laminae inside, right? All right? What would time do to that layer? If you had burrowing organisms in that rock, what would happen to that layer in short order? You would, what? Yeah, there would be holes, and then there would be holes in the holes, and then there'd be holes in the holes in the holes. Pretty soon there would be none of the original sedimentary structure present. How fast? Well, typical rates for sediment accumulation in rock based on radiometric dating are 10 centimeters per 1,000 years. Remember that number? 10 centimeters, that's that much, per 1,000 years. How fast do marine invertebrates burrow? Modern observed rates of homogenization are 1 year or less in the marine setting. So if you have some sediment on the bottom of the ocean and a year goes by and you measure that, you check that sediment a year later, you will find no internal structure. It will be completely homogenized in 1 year. Experimental rates, that is where you actually do this experiment in a tank where you can observe it, you get homogenization to a depth of 10 centimeters, about 4 inches, in less than an hour in some conditions with 10,000 preapulid worms or whatever they are. I've forgotten what kind of worms, but spionid worms, burrowing marine worms. Their densities may reach 16,000 to 60,000 per square meter. So it's not unrealistic to think that sediment that's deposited an hour ago may be completely homogenized an hour later. All right? Is that clear? Everybody understand that? If you have these burrowing organisms, you cannot maintain the structure in the sediment. So at these rates, all sediment deposited on a radiometrically determined time scale should be thoroughly homogenized. There should be no more sedimentary structures anywhere. Is that clear? 10 centimeters per 1,000 years. 1 year is total homogenization of 10 centimeters. Up to an hour, total homogenization. There should be no sedimentologists, because sedimentologists study the internal structures of sediments to determine how they got there. And if this burrowing had gone on for 1,000 years or 1,000,000 years, the internal structure would all be gone. There would be no sedimentary structures to study. Instead, we find homogenized sediments are exceedingly rare in the fossil record. Exceedingly rare, yes.
But not all burrowing organisms burrow in, per se, rocks and minerals. They burrow in just the topsoil layer.
4 centimeters, 10 centimeters, 4 inches, that's the top. That's what we're talking about. Richard Bromley put it this way, and I want you to pay a special attention to this. He is the author of the textbook on trace fossils. 100% bioturbation of the substrate is the natural end product of the activity of the endobenthos, the burrowing organisms. Okay, that's what you expect. Failure to reach 100% or the failure of that state to be preserved in the rock record are conditions that require explanation. So there's a lot of explaining to do on somebody's part, because the vast majority of the fossil record shows no burrowing whatsoever. Let's take a look. Here we are back in the Colorado Plateau. We're going to take a look at the whole geologic column in the Colorado Plateau. We'll start down here at the bottom. This is the Paleozoic, and here are the deposits that we're studying right here. And this is the thickness of it. This is, I don't know, 180 meters or 140 meters or something like that. And here is the amount of burrowing we found. And we need to look at the time scale, so let's take a look at that first. Here is a scale that gives you what kind of rocks we're talking about. This is a scale that tells you how much burrowing there is. Notice number 1, that's this column right here, is no burrowing or an occasional single burrow. Number 2 is some burrowing. Number 3 is significant disruption of the internal structure. And number 4 is homogenization. So if you see something in this column, 1, 2, can't read it. Oh, that's a question mark. Okay. Yeah, 1, 2, 3, 4. Question mark means you can't see what's in there. All of these sediments that you see here in this column show no significant burrowing. These show a small amount of burrowing. These show no burrowing. And that's the early Paleozoic. So let's just skip that and go on. This is understanding how to read the diagram. We've already done this one. Let's go to the upper Paleozoic here in the Permian. These are the deposits. This is the thickness. Somebody up front read that for me. What is it? 500 meters. You know how much sediment that is? 1,500 feet, 500 meters. And we went through every single centimeter of that looking for burrows. And guess what we found? Zip. Occasional burrow there, is it one burrow there, one burrow there, one burrow there. That means we did find burrows, so we could see them if they were there, but there's no burrowing there. All right, let's go on up. Here's the uppermost of the Paleozoic, and it looks like 50 meters maybe of sediment. Here are the deposits, and all of it's in column 1, no burrowing. All right, yes?
But I thought that bioturbation depends on which sedimentary environment we are in. For example, on the bank side you can find bioturbation, but in the riverbed you cannot because it's a moving water. So
these include all different kinds of environments, and they're all the same. So here you see in the lower Mesozoic, this is the Triassic, this is supposed to be marine. And here is the column that tells you what's there. It's all in column 1, and that is 500 meters. So that's 1,500 feet of sediment with no evidence of bioturbation. We move on up to the upper Triassic. Here we have the Chinle Formation. That's volcanic material. Probably somebody would say it was deposited on land. Well, guess what? What happens to sediments deposited on land? Does it stay? You deposit? Yeah, you get burrowing there. You get burrowing animals in it. If there's no animals there, you get plants growing there. If there are no plants, it blows away. So you have no evidence of bioturbation in, 250 meters of sediment in the the upper Triassic. Okay, we move up to the Jurassic. Here we see the Somerville Formation, I think it is. No bioturbation whatsoever. Move on up to the Jurassic and Cretaceous here, the Mesa Verde Formation and the Cedar Mountain Formation. No bioturbation. And folks, we looked at this centimeter by centimeter all the way through these thousands and thousands of meters. Here we have the Mancos Shale into the lower Cretaceous, and here you can see the vast majority, no bioturbation. Here is one spot where we found a little section that was homogenized. Well, guess what? That might be, you might think, well, that's bad. That's good, because if we didn't find it anywhere, we'd wonder if we could see it if it was there. But when we see it, we know it. People come from all over the world to see these spots. They make pilgrimages to see where you have homogenization going on. Here's a few other places in here, very tiny spots in the Mesa Verde Formation and the Mancos Shale, which showed level 3 and level 4, but the vast majority is in column 1. Yes?
Is that all of that liquor based on the layers of rock exposed? Like measuring what is already exposed
Uh-huh.
on the outside of it?
Yeah.
So would-
You want me to go through and dig my way all the way through that mountain so I can make sure it's not just at the surface?
Would that come from the consistency of that measurement there and the other spots that
Well-
are not exposed?
When geologists do core samples, they drill down away from the outcrop and they bring up cores of rock, and those cores of rock show no bioturbation also. Here we are in the Price Formation. It looks like, I don't know how many meters it is, a couple of 100 meters. At the risk of our lives, we climbed up. This is a highway outcrop. We climbed up and examined every square centimeter of this. We found a few places here where there was significant bioturbation. The vast majority showed no bioturbation whatsoever. Here is this is even more dangerous, the Castle Gate. We climbed this cliff and we looked at every square centimeter of that rock. I don't know how many meters it is, but a lot. And we found no bioturbation whatsoever. Up into the Upper Cretaceous, we have the Price River Formation, no bioturbation whatsoever. Into the Paleocene, Eocene, and we look at the Wasatch Formation. Where we could see into the Wasatch, there was no bioturbation. And then we looked at the Green River Formation, and where we could see, there was no bioturbation. So a careful centimeter by centimeter analysis of thousands of meters, tens of thousands of meters of sedimentary deposits across the Colorado Plateau shows a systematic and profound absence of features giving evidence for time. How can you explain that? If this sediment's accumulating at 10 centimeters per 1,000 years, that means there's plenty of time on anybody's scale for that sediment to be disturbed. The vast majority of those sediments show absolutely no indication of disturbance from the time they were laid down until they were buried by the next layer and the next layer and the next layer. The only reasonable way to preserve sedimentary features is by rapid deposition and burial consistent with short time. This suggests to me that maybe we ought to be thinking of some other way of explaining radioisotope ratios besides as meaning time as we understand it today. All right, that's number 2. Number 3, there's a general lack of erosion in the geologic record. This is a paper I gave at Geological Society of America a few years back. Does the Shinnerup Moenkopi contact represent a 10 million year depositional hiatus on the Colorado Plateau? I am standing and walking at the peril of my life on this line right there, which is a 10 million year hiatus in deposition according to standard geological reckoning. That is, this layer here and this layer here are separated by 10 million years, and yet it looks perfectly flat all the way along there. We have studied that all across the Colorado Plateau. These little red dots indicate places where we've taken photographs of this contact. Much of this work was done by helicopter because we couldn't get to it. The cliff is nearly vertical everywhere. And here is the situation. We have the Moenkopi Formation is lower Triassic, and then the Shinnerup that lies atop it is upper Triassic. So that gives you a difference of from 10 to 35 million years, depending on how you reckon it. 10 to 35 million years of depositional hiatus. But this is the line right here. Do you see any evidence of time there? It's perfectly flat. We have studied it all across this area. Right here, we're going to look at this area here. It's about 20 miles. And you can see in that 20 kilometers, you can follow even little layers all the way across that 20 miles. So there is no indication of major erosive activity in this deposit. Here you can see a place where there is some apparent erosion until you look at it a little more closely and you see that these layers are bent down. These layers are bent down. And the same thing is true over here. And it looks almost like this stuff pushed in there. So that's a bit of a mystery, but it doesn't look like it involves any time. It looks like these sediments were still soft when this cut into it. This is what's called a load cast. I'll teach you a little more sedimentology tonight. A load cast is a place where the overlying sediment has slumped down into the soft mud that's underneath. This is Moenkopi, this is Shinnerup, 35 million years between them, and this stuff is still soft. Soft enough to produce load casts when this sandstone slumped down into the mud that's underneath. Here you can see some more load casts here where they push down into the mud. This is a outcrop that we studied in detail, and you see that little white line right there at the contact. This is the Shinnerup conglomerate up here. This is the Moenkopi Formation down here. Right there at the contact, there's a little white line. We'll take a look at that. Here it is. It's a porcelainite, a very fine-grained mudstone, and watch what happens with it. Here's the bottom of that sandstone right here. So we're looking up at this rock and its relationship to this white layer. Here's the bottom of that rock. You can see places where the sand has squished down into the white layer. Do you see that? See that there? See that there? Over here it's pushed down, over here it's pushed down. This is places where that sand has pushed down through the white layer over here, but into the underlying material over here. Those are all load casts. Now here's another case. This is sandstone. This is sandstone. This is that white layer. The white layer has been squished up into the load casts. This side and this side are load casts, and it's pushed that stuff in there. That stuff had to be soft when those layers were deposited. Clearly, Moenkopi did not sit for 10 to 35 million years without erosion or deposition or lithification. If it was lithified, then it would have been hard. If it was eroded, then we'd see it was missing. If more had been deposited, we'd find the deposition. This isn't an isolated example. There are other more extreme examples. For example, in Grand Canyon, there's 140 million years between two layers that in many places in the canyon are perfectly flat. These episodes of non-deposition are most readily explained by a model of rapid deposition and burial consistent with short time. Erosional rates. Those of you who have heard about the landslide that occurred in California, that's not an unusual event. It happens all the time. California is moving toward Florida as fast as it can pedal at about 0.75 to 1.5 feet per year on average. At this rate, California beaches will be in Florida in less than 15 million years. Do you see what I'm saying there? All the way across North America at the current rates of erosion. Conservative and realistic rates of continental erosion based on modern erosion rates suggest all of North America will be eroded to sea level in between 10 and 33 million years. All of North America will be at sea level. Colorado, Wyoming, we're at 4,300 feet here. We're going to be at sea level if there is 10 million years, in 10 million years. Are we at sea level? Has there been 10 million years? It doesn't seem so, does it? So that 10 million years that I showed you between those two layers, where they're supposed to be represented 10 million years, that's enough time to erode all of North America to sea level and there's a flat contact between these two deposits. How do you explain that? Current erosion rates determined by a wide variety of indicators would have North America eroded to sea level 20 to 60 times in 600 million radiometric years that life is supposed to have been on the Earth. If North America had been eroded to sea level once, where would all the sediments that have fossils in them be? Out in the ocean. If it was 10 times, where would they be? Out in the ocean. If it's 60 times, where would all of our sediments be? But you go to Grand Canyon, what do you see? They're all there. The sediments are still all there. Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and recent. They're all there. If North America had been eroded even once, we wouldn't be able to find most of those sediments. This phenomenon is best explained by short time. And last, the current status of the survival of biomolecules. It's still in flux. We don't have ultimate answers on this yet, but it's an ongoing study. Mary Schweitzer has documented existence of tissues, proteins, blood cells in bones that are supposed to be 65 million years. Many other examples of biomolecules lasting far beyond their physical chemical limits can be cited. In fact, we're doing some of that work ourselves. How can you explain the existence of a biomolecule that has a half-life of 55 years? How can you explain that it's still there after 65 million years? If it has a half-life of 17,000 years, which is what we cited last night for biomolecules that are frozen, 17,000 years, in 10 half-lives, the biomolecules are all gone. 10 half-lives is 170,000 years. 100 half-lives is 1.7 million years. 1,000 half-lives is 17 million years. And we expect that possibly biomolecules could not last 10 half-lives. How do we explain the presence of biomolecules in fossils that are supposed to be very old? The best, most clear-cut answer to the question is radiometric dating is not giving us the correct answer for time. Here you can see some of those biomolecules. These are tissues that were extracted from the bone of T-Rex, and you can see all the structures that were there. The tissues are springy. They can be stretched and released. Here you can see some blood vessels, and they have things in them that look like red blood cells right there. Right there. These are some actual osteocytes that were derived from T-Rex tissues. This is osteoclast that breaks down bone tissue, and it was isolated from bone. Here is a vessel that was isolated from that bone by dissolving the bone in ethylene diamine tetraacetic acid. Here is another blood vessel with a red blood cell still in it. After 65 million years, when biomolecules cannot, by any stretch of the imagination, last more than 100,000 years. Yes?
How are these tissues still preserved, even though, because it was thousands of years if we went by the flood model, how would these tissues still be preserved for that long?
The British Museum has some very old specimens that were collected hundreds and hundreds of years ago that they have examined, and their tissues are still pretty much intact. They're breaking down, but they can't see the breakdown because it's at a molecular level. So the tissues are still there. So it's not inconceivable that they could last for thousands of years. It is inconceivable to me that they could last for millions of years. And 65 million years is 65 times less likely to last than a million years. And a million years is 100 times less likely to last than 10,000 years, and so on. So you get into this numbers game, but it's pretty clear to me that you do not expect to find blood vessels with blood cells intact after more than a few thousand years. These discoveries make the conventional interpretation of the meaning of radioisotope ratios untenable in my book. Continuing discoveries of biomolecules not only make conventional scientists uncomfortable, but will require them to fight vigorously against their acceptance. Mary Schweitzer, even though she's an evolutionist, even though she believes in long ages, she happens to be a Christian, but that's a problem for her because she doesn't like the consequences of what she's finding. But these scientists have attacked her with vitriol because she's finding these things and claiming they're in the bone. So they've tried every ruse imaginable to try to prevent her from being successful in publishing her work. But it's still widely accepted that what she is finding is there. The best understanding of this evidence is that current interpretations of the meaning of radioisotope ratios are wrong and new explanations should be sought. You want to get a Nobel Prize? Go educate yourself in radiometric dating and figure out some other explanation besides raw time. So sedimentology indicates rates of deposition, general absence of bioturbation or interstratal erosion, absence of evidence for time between units, and by other features that are radiometrically determined time is not giving us correct values for real time. The survival of biomolecules far beyond experimental values likewise challenges the radiometrically determined dates. Therefore, the meaning of radioisotope distribution should be reevaluated. Any questions? Yes.
How much has the bioturbation thing been studied by other scientists as well?
Well, there are people that make their living doing that, but they're thinking within their own paradigm. They're not thinking about what this really means, the fact that they have to drive 50 miles to find some bioturbation. And there are lots of sediments that have bioturbation in them. Bioturbation can happen very fast. If you bring in some sediment that has bioturbators in it, and you would expect that to be the case, then those bioturbators can set to work right away and start burrowing. But when you look at the overall picture, as I said, sedimentologists should not have a job if radiometric time is correct, because those sediments should have had all the internal structure erased. Most of these sediments that I showed you are marine sediments. Most of them are. But even the ones that are not marine are subjected to all kinds of vagaries in nature that would disrupt the structures over time. So if you have 1,000 years for this much sediment to sit still, it's not going to sit still. It's going to be moved and remobilized and transported and deposited again, and the internal structure is going to be gone. Or it's going to be subjected to a root zone where the roots grow down into it and disrupt the sediment, and it's gone. Or something else. But you do not expect, as Richard Bromley correctly asserts, any sediment that does not show 100% bioturbation has to be explained. So the explanation is not on us. The burden is on them to explain why their stuff still shows internal structure. And they are not going to have an explanation. Anybody else? Now, I haven't answered the question why radiometric dating seems to work. Why does it give us correct dates that fit with the stratigraphy? Is somebody just manipulating the data, or do the data speak for themselves? And that's a question that I don't even feel qualified to answer. I know that when you see a student's dissertation and you look, the students usually want to report everything they did because this is their big chance to report everything they did. So they put in every date. And you can see in these theses that a lot of dates don't come out right. You don't see that in the published papers because they filter out all the bad ones, so that they don't corrupt their publications. So that's certainly a consideration, but I don't think that's the whole answer. I think there's some systematic reason why radiometric dates are giving us long ages, but it does not match what we see in the sedimentary record.